Hello, welcome to the real broadcast. So the last video I did was about getting ready to code, how to create the thumbnail and the image, and now we're actually going to do the code. The work begins now. So look if I can talk to Tippy. Tippy can help us do this, which is my AI buddy. Um, where's my project? Yeah, okay. Well, you can't actually see what I'm doing. Okay, so what I'm doing now, this is the project. Everything's in here. It's been awesome. Everything I've done, everything I've said, has been recorded. And I'm probably going to broadcast this whole entire how this thing's going to be put together. So we're basically building a price compare app, but with several features. But one of the key things we need to do is scrape the products from different websites to get the product information into the database. The first thing we're going to do is start up Docker, because that's where the data is. It's in the Docker database. Okay, we've got did it start it? I don't see it there. Usually there is a Docker icon. Ah, it's slow. There's a delay, but I got it. Okay, yeah, we're good. We are good. We are good. Yeah. All right. Let's make this thing work. So, as I was saying, we need to make this thing work. Of course, we need to make this thing work. But what I mean is, we need to get the data and put it into the database. So let's do it. Where do we even begin? All right. So the code that I did yesterday. So you can see the main thing for crawling is actually, this is the route. So you hit this route, this is where it begins. And let's first just make sure that all this code is committed. Okay, there's no changes, that's good. So everything is committed to the database. That's good. So maybe we can try and understand, because basically the products are scraped, the scraping code actually works. Got that going yesterday. This is the route that's hit. As soon as you put in this route name and hit this endpoint, and then oh, here it is here. This is the actual code that does the scraping. Okay, we can actually get rid of these comments. So let's do that first. This is the old code. Delete. All that would take me so long to write. Get it perfect. The AI can get it done quicker than me. It's my job. It's actually a lot smaller than what it was before. Why is that? Maybe we should not delete that comment. What I'm going to do is keep it because why is it so smaller? But actually, it's a lot. It's a lot smaller. Look, it's only importing one thing. Wow, is that it? That's the whole code to do the crawling. Let's go and talk to Tippy and ask him to explain himself. Explain the code. So just in case he's forgotten something, you need to remind him. Let's copy this code here. I can't be bothered reading it, so what we're going to do, for now anyway, we're going to give that to Tippy, and Tippy will explain this. Anyway, I'm just having a relapse here. Bear with me. Okay, we're going to get Tippy to explain the code. So I'm just pasting the code for the caller. We'll give him that. Just to remind him of what we did yesterday. It's just like a human. It may forget. Sometimes it does. I may not remember everything from yesterday. So I give it both pieces of code. Then let's try to explain it. Yo, Tippy, explain this code. So we're going to get the AI to explain himself. Yes, get him to explain it.
All right, let's break this down slowly, out loud, so it's clear what's happening in this crawler code. First, the library file, lib/crawl woolworths.ts. Here, the goal is to fetch HTML pages from Woolworths URLs in a way that looks like a real browser, so the site doesn't immediately block the request. We set up browser headers. This is a collection of HTTP headers that mimic what Chrome would send. It includes a user agent string, accepted content types, language preferences, and sec fetch hints that make the request look like it came from a human browsing normally. We define a crawl result type that records which URL was fetched, the HTTP status code, the content type returned, the number of bytes in the response, and a small snippet of the page, the first 220 characters cleaned up. The fetch HTML function does the real work. It takes a URL and a timeout, sets up an abort controller, and uses fetch with those fake browser headers. If the site responds, it reads the text, captures the metadata, and returns it as a crawl result. If the site hangs too long, the timeout aborts the request. The crawl Woolworths function then loops through all the seed URLs. For each, it tries fetch HTML. If it succeeds, great. If it fails, network error, timeout, blocked request, it catches the error and still returns a crawl result, but with status 0 and a snippet containing the error name and message. That way, you always get structured output for every input URL. Next, the API route, apps API crawl woolworths/root.ts. This is the Next.js server endpoint that clients call. It uses Zod to validate the incoming payload. The expected body must include auth key, a string, seed URLs, an array of valid URLs, at least one, optional fields like max pages and delays. They're placeholders for future throttling. The code compares the provided auth key against a hard code.
Okay, this is too. We need to get it, explain it in more detail, even. Explain it in more detail and show the code as well that is explaining. Yo, Tippy, can you explain that code in more detail and also explain it in more detail and also show the code when you're explaining it, show the piece of code as well. Yep, it's better. Let's do it in pieces as well. Hey, Tippy, let's make this like a learning experience. So when you just first of all give an overall summary of the crawler and how it works, and then let's dive deeper. Explain each main piece one by one. Wait for me to respond. If I say I got it, continue to the next question. If I say explain more or show more information, then dive even deeper. I may have a question about what you are trying to explain to me. So I want you to branch off, basically. We're going down rabbit hole mode. But rabbit hole mode for a learning experience, a learning journey of new techniques that I'm unaware of. Come up for a name for it. So we can use this technique in the future and commit it to memory that I want you to do this. So wait for my output. Wait for me to explain one. First of all, give a brief summary of what you're explaining, not a brief, a semi-brief, and then in steps, each main concept of the code. Show the code first, and then under the code, have the explanation of what that does for one piece, then wait for me to give you direction. Either I'll say, okay, I got it, or let's branch off to explain. Maybe you branch off and to go into even more depth for that item. And we don't need numbers for this. Okay, let's go. I wonder if I can actually understand it. Of course I can understand. Well, that's a long explanation. So we want to get it to explain the code. This is the code, the crawler code. I don't feel like continuing until I could read it myself and try and understand it, but it wrote it, so it can explain it.
Torn up spine, still in the gym like force divine, no fake hype. I'm moving silence, but my code hits back with pure defiance. Being that puncher gonna rip through time. I don't need a badge or a suit to shine. No degree, just clarity and drive. I built this beast to stay alive. Fuck the limits, I make my lane. Cut through noise like a motherfucking train. They sleep on me, now I own the track. They're fake ass titles, I'm looking back.
But it's a talk. Move the speaker button back,
Sweet,
ChatGPT.
switching to our new teaching flow. Rabbit hole, branch and drill, saved. Here's the semi-brief overview, then we'll tackle the first piece and pause for you. Semi-brief overview. This crawler exposes a post-API endpoint that takes an auth key and a list of Woolworth's URLs. The endpoint validates the payload, checks the key, then calls a library function that fetches each page using browser-like headers and a per-request timeout. Each fetch returns a compact result with status, content type, byte size, and a trimmed HTML snippet, so you can quickly see if you got the real page or a block consent wall. The API responds with all per URL results. If literally every fetch failed, it returns a 502, so clients know the upstream is the problem rather than your server code. Piece 1, browser Y headers and result shape, code first. You can see the code in our conversation history. These headers make each request look like a normal top-level browser navigation from Chrome on Mac OS, which helps bypass basic bot filters. The sec fetch dry hints and the user agent are especially important signals to CDNs and bot guards. The crawl result type defines the minimal facts you need for quick diagnosis without storing the whole HTML, which URL you hit, whether it succeeded, what kind of content it was, how big it was, and a short, clean snippet to eyeball whether you landed.
Explain this thing in more detail for each property. For like we have no cache, explain that, explain upgrade and secure, sec fetch site, explain that, sec fetch mode, all of the properties, sec fetch user, sec fetch dest, I guess that means destination, and also the values as well for those options. Cache control, accept language, I guess I know what that one is, and the main accept property, and the entire parameters in there, explain them in detail. Explain this whole thing in detail. It's this browser headers. So I know we're faking it, that we're trying to fake that we're a real human before we make the request. Even the input, like I'm unfamiliar with that. Really? Incoming HTTP headers. Is it incoming from HTTP? I guess that just combines more headers. And then down the bottom here, we've got export type crawl result. Yeah, so we need that as well. Actually, I didn't switch my screen. Okay, so yeah, explain this in more detail. Make this a bullet pointed list and use some fancy icons. All right, you can't see my screen, but I was just getting it to talking about that piece of code there, and we needed to explain it in depth. Because this is new to me. Maybe it's new to you too. Actually, we should use numbered points so I can get it to. So I can drill even further. I can easily tell it what one to explain more. Actually, Tippy, drop the icons and use a numbered point list so I can easily get you to. I can easily refer you to a point that I want you to drill in on. So this is how we can get. Did I actually get that? Tippy, drop the idea about bulletin points with thumbnails. Use numbered points so I can easily refer you to an item I'd like you to drill more on. Okay, let's try that. Drill more on. Okay. We have numbered points. Now, okay, let's just get it to read it out loud.
Got it? We'll use numbered points instead of bullet icons for these header plus type explanations. That way you can just say explain point 3 more and I'll branch right into it. Here's the breakdown of the browser headers and the crawl result type. You can see the code in our conversation history. Detailed explanation. 1. User agent. Pretends we are Chrome 124 on macOS. This is the single most important string for passing as a real browser. 2. Accept declares acceptable MIME types, text HTML, application XHTML plus XML, application XML with Q equals 0.9 weight, image AVF, image WebP, and then anything with lower priority Q 0.8. 3. Accept language, lists language preferences. First is NNZ, New Zealand English, then plain Eon with slightly less priority, 0.9. 4. Cache control, no cache. Tells the server and proxies to revalidate instead of serving stale cached content. Pragma, no cache and older HTTP 1.0 header still included for compatibility. 6. Upgrade insecure requests. 1. Request the secure HTTPS version if available. 7. Secfetch site none means this request isn't cross-site or embedded. Looks like the user typed the URL or clicked a bookmark. 8. Secfetch mode navigate signals this is a top-level navigation, not a sub-resource fetch. 9. Secfetch user 1 only included on true user-initiated navigations. Strong real browser fingerprint. 10. Secfetch dest document says the destination type is a full HTML document, not an image or script. 11. Incoming HTTP headers type comes from Node's HTTP module, normally used to describe headers coming into your server. We cast our custom headers to it just to keep TypeScript happy. 12. Crawl result type. The shape of each crawl output, URL, the page requested, status, HTTP status code, or 0 if failed, content type, value of the content type header, if any, bytes, size of the body in bytes, snippet, first 220 characters of the body, whitespace normalized. Now you can say something like, explain point 2 more, or go deeper on 710 as a group, and I'll branch off.
Explain each of these in even further detail and explain each property, the value. And if the value has sub-properties, explain each one of those too in more detail, a lot more detail. Do it again. Okay, so we're just trying to get it to explain these points in more detail. There's a lot going on in this little piece of code here. So with the user agent, so there's like iPad, Mac, or whatever, PC. Where's the value? What value is it set to? That's the value there. Ah, maybe before continuing, you should do the crawler for pack and save before saving it to the database. Like saving it to the database is the easy piece. But maybe if we have a full, but if we save it to the database, then the data can obviously be seen. Is it finished yet? No. It's just got a full explanation. Come on. Okay, I think it's just versions. Let's open up a new window here. Okay, it's a new window. What the? This version. Anyway, so we need a new window because it's slowing down. Here we go. Whoa, so it's explaining itself. Okay, let's get it to figure it out because we want to know what we're doing here. We're trying to get it to explain this crawler code here that is from that crawls the website. It actually gets the data from the website that created this code, and now I'm trying to get my head around it to work out what it's doing. I could go for it and read it, but actually this piece here, this piece of the code, is actually, there's a lot going on here. Like this sec fetch user, this stuff I don't know. I've never used it, never seen it. No cache, that's pretty obvious. Obvious, I guess. This is not caching it on their end. Or is that on my end? Basically, this is the HTTP header that it sends through. It just mocks it, makes it look like we're a real person making the post request. Isn't it a GET request, actually? To the Woolworths website, and then it's going to show the products. So we can eventually we've got to get the products into the database. But I want I want Tippy. I call him Tippy. This the artificial intelligence thingy, and I want him to explain this code. So let's do that. I'll read it out loud.
Awesome. Here's a deeper pass on just the browser headers and the crawl result type. I'll show the code first, then give numbered explanations so you can say explain 7.3 more, etc. You can see the code in our conversation history.
Actually,
Go to user agent 1.1.
Actually, a better way of doing this is actually to have a little snippet of code. See this piece here, user agent? Paste this piece. See the value? It needs to be exactly in this format. Somehow it knows. Here's the value. It'd be nice to see the piece of code right beside each point. So I'm going to get it to redisplay this information in the way I want. So Tippy, actually I've got an idea. Let's break this rabbit hole technique for teaching me how this code is working in even a smarter way. So do you know how I told you to break those points down even more? Like for 1, 2, and 3? So we're going down a rabbit hole here. So this is actually point, whatever point it is, let's use sub-points because we're going down one level. So this is like point 2, point 1, 2.2, 2.3. So we can keep track where we are because we're going down a rabbit hole. And also, beside each point that we're going through, show the code as well. Show the code above the point. No, first say like the property name in this case. So user agent, that's the property name. Under the user, and under that, show the actual code for user agent, for example. And in this case, it has the show the property name and the value for the code. So in this case, it's user agent mozzarella 5.50 whatever round bracket Macintosh semicolon Intel. Just show the whole value, and do that for each of these, every one of these options. So there's that 1 to 12. Okay, commit this to memory and show the information again. So we're drilling. So it's a good way to learn it, right? Yeah. So redisplay the information again in the format that I just said. Okay, let's send that through. So we're asking it to display the information in the way I want. And you may notice I asked it to commit it to memory. And there's just a bunch of gobbledygook there. And I set it in. Because I was thinking while I was saying it. And I didn't think up front totally. And I came up with ideas why I was saying it. Oh my good. Did it? Yeah. Good. There you go. Now it's doing it. It's sort of doing it. Actually, it's not totally doing it. Let's see here. It's it put the title as I said at the first. Then it had the comment. 1. What the hell? Oh. Oh, okay. It made a subpoint for each property. Well, that's an idea, but I didn't actually want it to do that. Yo, Tippy, I actually didn't want you to do this. What I meant was, for the subpoints, in this case, you're explaining each property, aren't you? No, you're explaining each. Oh, how do we say that even? Yeah, you are explaining each property to me. And the cases, the properties are user agent accept language, cache control. Yeah, these are the properties. Or are they objects? That doesn't matter, really. I guess they are key names. They are property names. That's what they are. Okay, we're going to call these things property names, and they have a property value. Okay, so I need you to explain each property name fully, and the property value fully, and rabbit hole mode. So only display one at a time and wait for my response. If you need to drill down further, then you branch off with the numbering system. On the outside, we've got point 1, 2, 3, whatever. So if it's a sub point, it should be 1.1, and then 1.1.1, or 1.1.1.2, etc. We're going deeper and deeper down the rabbit hole, branching off. In the case of like accept, the accept property, that has a very complex, not that complex, but it has several properties. Some of these properties can be considered an object. For example, Q equals 0.9. And in that case, yeah, explain it. You got to explain each property. That there are several properties, explain each one by one, and wait for my output. Don't just list them all. And go down the rabbit hole again. Basically, go down the rabbit hole for each property if there are more than one. That's what I mean. Okay, I'll put this again, and then let's try. Okay, I don't know if it got that. I don't even know. Did I actually even understand that myself? Let's try. Well, it's gonna actually get that. It's actually pretty complicated. Of course, it can get it. Okay, I guess that's what I meant. Do one property at a time. Because I need to remember this. Okay, so it's frozen again, so let's get out of there, go back in. Da 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 da. Need a faster Mac, I need a faster Mac. Here we go, better than me, man project. Huh? I think it got it there. Oh, user agent. What is proper? Here we go. Here's the code. What this property is. The user agent header is a legacy identification string that websites CDN. I know what that means, but I forgot. And bot guards need to infer the client's browser rendering engine. Operating systems and sometimes devices that heavily influences allow deny rules and content variants. Why we set the value. Okay, breaking the value down. Nice. I think that's actually how we want to do it. Okay, read out loud.
Locked in. We'll do one property at a time, code first, then hierarchical drill. 1, 1.1, 1.1.1. I'll stop after this property and wait for your queue to go deeper or move to the next property. Number 1, property name, user agent. You can see the code in our conversation history, bot1. What this property is. The user agent header is a legacy identification string that websites, CDNs, and bot guards read to infer the client's browser rendering engine, operating system, and sometimes device class. It heavily influences allow deny rules and content variants. 1.1, why we set this value. We're imitating a modern Chrome on Mac OS, so the request profile matches a real top-level browser navigation. Many bot walls cross-check user agent against the secfetch family. A realistic, internally consistent combination reduces blocks. 1.2, breaking down the value. 1.2.1, Mozilla 5.0, historical compatibility prefix used by essentially all modern browsers, signals, I'm a mainstream browser. 1.2.2 Macintosh, Intel Mac OS X 1015 score 7, platform tuple indicating desktop Mac, Intel CPU, Mac OS 10.57, Catalina. 1.2.3 Apple WebKit 537.36, rendering engine lineage version, WebKit number shared across Chromium Safari lineages. 1.4 KHTML like Gecko, legacy tokens kept for old UA sniffers expecting Netscape Gecko heritage. 1.2.5 Chrome 124.0.0, the primary browser brand plus version we want the server to recognize, Chromium 124. 1.2.6 Safari 5537.36, compatibility token retained because many sniffers historically checked for a Safari fragment even on Chromium UAs. 1.3 How servers actually use it. 1.3.1 Feature gating, crude UA sniffing to decide which code path to send, legacy versus modern. 1.3.2 Fraud bot rules. WAF CDN rules reject uncommon or internally inconsistent UAs, e.g. mobile UA plus desktop secfetch. 1.3.3 AB and personalization, sometimes used to segment experiments or deliver device-specific assets. Reply with one of these and I'll proceed accordingly. Go deeper 1.2.5 or any subnumber to drill that fragment further. Got it. To move to the next property, except branch 1.3.2 if you want examples of WAF checks and pitfalls.
Maybe you need some more info on this point here. I call this rabbit hole mode because they're going down a rabbit hole to learn this stuff. Legacy tokens kept for old UI sniffers expecting Netscape Gecko. Gecko was a web browser. So this point, if I just paste that, it will work out that I want more information about that. I don't need to say anything else. Let's see. Yep, but it knew what I wanted. Whoa, we're going to right down a rabbit hole here.
All right, diving into 1.2.4, that's the KHTML, like Gecko, fragment inside the user agent value. Property fragment under user agent. You can see the code in our conversation history. Our 1.2.4 explanation. 1.224.1, what it is, a legacy compatibility token. KHTML was the engine behind Conqueror early Linux browser. Gecko was the engine behind Mozilla Firefox.
I pressed the button. Put the button
All right,
back.
diving into
ChatGPT.
1.2.4, that's the KHTML, like Gecko, fragment inside the user agent value. property fragment under user agent. You can see the code in our conversation history. Our 1.2.4 explanation. 1.224.1, what it is, a legacy compatibility token. KHTML was the engine behind Conqueror early Linux browser. Gecko was the engine behind Mozilla Firefox. Chrome inherited WebKit from KHTML. So early, Chromium added this string to reassure sites that did strict UA sniffing. 1.24.2, why like Gecko? Back in the 2000s, many websites only worked if they detected Gecko, Mozilla in the UA. To avoid being locked out, WebKit browsers said they were like Gecko. 1.43, why it still exists today. Even though hardly any modern site depends on it, browsers keep it because removing would break old enterprise apps and brittle bot rules that parse UA strings. 1.2.4, how servers use it now? Mostly ignored, but some parsers split UA into tokens and expect like Gecko to be there. Its absence can make a UA look suspicious or non-standard. Do you want me to drill down deeper, e.g. 1.2.4.2, history of KHTML versus Gecko wars, how Apple forked KHTML into WebKit, how Chrome then forked WebKit into Blink, or is this level enough and we move to 1.2.5, Chrome 0.24?
Oh, we can actually go so deep into this. Let's skip that. Just say next, which will take us to the next point, out of this rabbit hole and back up one level. It went to explain this value here. Chrome. Wait a second. So the piece of code we're explaining is this one. Wait a second. Where is it getting Chrome from? I think we're still explaining user agent. Oh, it's going to explain this property here, Chrome. I didn't mean for it to do that. I wanted to get out of this rabbit hole. Let me tell it. If I just say the word up, that means go up one level and to the next object or property. Let's get it to commit that to memory. Commit this instruction to memory for rabbit hole mode for learning. Shit. Okay, let's get it to remember that. Commit it to memory when I want to learn things. Okay, it's remembered it. Okay, now if I just say up, that means to go up one level. To go back to the next property. Now it's explaining Safari. Is that correct? I don't think that we are actually up one level. Okay, I guess we're still down on a level. No, let's try and go up again. We are still in a rabbit hole. We want to go up one level of information. Up. Tippy, go up. Okay, we're going to go up one more level. Okay, if Rickens understands, point 2, accept. And you can see here, we're actually down the rabbit hole. I'm pretty sure that is correct. Then we just double check. Accept. Oh, actually, we do. Actually, I do want it to explain those things. Okay. Okay. Actually, I wanted to go back to where it was. I think I need to tell it to train it. If I say back, that means I made a mistake and I want it to go back down the rabbit hole to where it was. Well, Tippy, when we're in rabbit hole mode, if I say back, that means I actually made a mistake and I want you to go back to where we were. So Tippy, go back. So we wanted to go back. I forgot to tell it to commit it to memory to make sure, because I don't want to tell this again, so you make sure you tell it. Go Tippy, commit this to memory. Therefore, tomorrow or any other time when I go back, it will remember. Okay, back. Under the last navigation step, return to where you were. Yes. Now let's just use the word back now, because I want to go back to where we were, which was just explaining the properties of user agent. And we need to know we were on user agent as well. Just thinking. Did it internet issue, or was this got it? Okay, it's trying to go back one step. I wanted to go back to explaining Safari property. Is that correct? Let's see. No, we've got the white screen of death almost. Anyway, looks like it's crashing again. We run out of memory, so just close it. Just how to do it. Open a new tab, go back until I can get a new computer. Go back to my main project. User agent 1 point. It's the top chat. So you organize all this information by projects. Okay, let's just get it to read it out loud. Is it correct?
Back we go, restored to 1.2.6 inside user agent. 1.2.6, Safari 537.36. You can see the code in our conversation history, .1.26.1, what it is. A compatibility token advertising Safari lineage. Chrome keeps it for legacy UA sniffers. 1.6.2 structure. Safari equals brand token browsers historically checked for. 537.36 version-like number aligned with old WebKit numbering. 1.2.63 why Chrome includes it. Early sites gated features on seeing Safari. Keeping this avoids breaking brittle UA checks and reduces bot suspicion. 1.264 modern server usage. Mostly ignored today, but absence can look unusual to legacy parsers. Tell me how you want to proceed. Say go deeper 1.26.2 and I'll unpack the 537.36 lineage, WebKit blink history, why the number persists.
Look at this. There's just this random number that pops up. Well, here's the number. It's analyzing this property here, which is part of the user agent. Interesting. Do we need to go deeper? Maybe, yeah. Who's interested in that? Do we even need to know? Do we need to know this? Here's a magic number. 537.36. If I just paste this number here, actually, if I just say deeper or branch, I just paste that number and it will know that I want to go deeper into that version number. But who's the person who came up with it? Everything. There's no way of knowing everything in that code. Is this called getting sidetracked? Here you go. It's getting even more information now about why it's got that number. I don't even need to.
1.26.2, the numeric part of the Safari/537.36 fragment in the user agent. Property fragment under user agent. You can see the code in our conversation history. 1.2.6.2, the 537.36 value. 1.6.2.1, what it represents. This number ties back to the WebKit rendering engine versioning system. Even though Chrome forked from WebKit into Blink in 2013, it still carries a WebKit-style number in its UA string for compatibility. 1.2.62.2, why 537 specifically? WebKit had major version bumps through the 500s, e.g. Safari 5, WebKit 533. By the time Chrome stabilized around its own identity, the engine it used, WebKit 537.x, was the current line. Chrome froze this number in its UA string, even as it switched to Blink to avoid confusing legacy sniffers. 1.26.2.3, the 0.36 minor version. This was the minor increment in the WebKit line when the UA string template was standardized. Chrome hasn't updated it in years. Most Chrome UAs today still end with 537.36. 1.2.6.2.4, why it persists. Sites and CDNs had baked-in parsing rules that expected a Safari WebKit fragment with a 53x.xx number. Removing or changing it would have broken countless sites. So Chrome keeps sending Safari 537.36 indefinitely, even though it's Blink powered.
Okay, let's go up one level. Property name accept. Here's the code. Application. Okay, so
Climbing up one level, we've now finished the deep dive into one user agent and all its fragments, 1.2.1 through 1.2.6. Next top level property is number 2, property name acceptl. You can see the code in our conversation history. This value is a comma-separated list of media types, some with Q, quality weights. Each item can be treated as a subproperty we'll drill into. 2.1 is to HTML, 2.2 application XHTML plus XML minus 2.3 equals application XML, QRL 0.9, minus 2.4 it's image AVIF, 2.5 is image WebP, 2.6 equals tire QRL 0.8. Do you want me to start with 2.1 equals text HTML and go deep rabbit hole style into that one?
yeah, I guess so. Accept. Who's accepting it? So when the request is made, we set this header. I think that means the server's going to spit back. We're telling the server when it hits the endpoint that it wants to get back text or HTML. And the application that is making this request is XML or HTML. I don't know what that X is doing there. And the application, there's some more information about XML. I think this is the version. Here it goes. This means quality 9. So there's a quality of the XML, which is 9. We also accept images. And I don't know what that means there. That AVIF. I don't know what this acronym means or what it does. There's basically 2 types of images we accept. I was speaking like JPG or PNG, but not. What is a WebP? Wouldn't have a clue. This looks like some type of wildcard. */* any of something of a quality that's 8. In this case, I think I just want to get it to explain all of them at one go. So we can just say explain 2.12, 2.6 in one go. Well, it's gonna say all these numbers. I don't want it to just say the numbers. It's hard to, because I want to get it to read out loud. Oh no, I can just say it now because it knows when I say it refers to the thing I was just talking about. So it's got that context in its memory. This is how it knows how to respond. So it's going to remove the numbers because I don't want it to explain it with the numbers. There you go. There's a nice block of text. And we may need to get it to slow it down because it may say it too quickly. Let's try.
All right, let's walk through the accept property smoothly without numbered points, just clear flowing explanation. Property name, accept. You can see the code in our conversation history. The accept header is a way for the client to tell the server what kinds of content it can handle and how much it prefers each one. It starts with text HTML, which is the default format for normal web pages. That's what browsers want most of the time, so it's at the very top. Next is applications like XHTML plus XML, which is the XML version of HTML. Some sites, especially older ones or ones built on strict XML systems, may serve pages in XHTML. Chrome supports that too, so it's included at the same priority as normal HTML. After that, you see applications XML Q.9. This means the browser is also okay with raw XML documents like RSS or Atom feeds, but it marks them as slightly less preferred using the Q = 0.9 weight. A Q value is a quality factor between 0 and 1, with 1 meaning I want this the most. So here HTML and XHTML are slightly higher in preference than plain XML. The next two are image formats, image/AVF and image WebP. These are modern compressed image formats that Chrome can render natively. By listing them, the browser gives servers permission to send those formats in navigations if they're available, instead of older formats like JPEG or PNG. Finally, there's Q = 0.8. This is the wild card. It means I'll accept any type of content, but with lower preference. It's a fallback, ensuring that if a server replies with something unusual, the browser won't just fail. Instead, it will attempt to process it, but the server knows that wasn't the browser's first choice. In short, this header tells the server, please send HTML if you can, XHTML is fine too, XML is acceptable but not as good, I can handle modern image formats like AVF and WebP, and if nothing else matches, I'll take anything you've got. Do you want me to branch deeper into the Q-weight system, since that's the trickiest part, or should we move up to the next property? Accept language.
Whoa, that's actually a pretty good explanation. You guys get that? I sort of do. So when you're at your browser and you visit a website, we send this accept thing in the header, which is the top piece of information that the server is going to process. So what I'm saying is we got text HTML, we accept text or HTML, but we also accept XML, and this we're going to get to explain this weight thing more. But we also accept these two other types of web images. as well, and this thing's a wildcard. So if it can't return any of this stuff, if the server cannot return any of that stuff, then it will just try and return anything. And then we've got this queue thing here, which it was talking about, which is a weight. That's not quantity. I'm saying that wrong. Anyway, the bigger this number, the higher priority that these things have. So this is an 8. This is 8. This one's 9. So this has a higher priority. So it's only going to return one of these things. And you can see that this one has a higher priority than this wildcard. So but it can't return this, which is 9, so it has high priority. Then it will go to the one of less priority, which is this, which is the wildcard. And it will return this one instead. Well, that makes sense to me. We could get it to explain this one a little bit more. Might as well. Set language. Okay, let's branch into Q. I can't be bothered typing it. I'll say it. Branch into Q. Let's branch into Q. I didn't actually get it. Did you see that? Just disappeared my text. Try again. Branch into Q. Use that Q, but get this one just to make sure. Okay, we're not going deeper into the rabbit hole after this. So just that little piece of text, I can show you that we are analyzing right now. This is called analyzing. It's just this piece. That's the piece. This is the piece. If you get all this right, if you get any of this wrong, basically, then you can't crawl the Woolworths website. So we are analyzing that. So we're doing the accept piece, and we're doing, what the hell does this little query thingy do? Huh? So we are analyzing what the hell that does. And it's coming up with like a whole page of text to explain what this queue does. Now let's get it to speak out loud for us.
All right, let's branch into the queue weight system that shows up in the accept header values like applications.xml and quocache q equals 0.8. What Q is? The Q stands for quality factor. It's a way for the client, the browser, to rank its preferences when multiple content types could match. It's always a decimal between 0 and 1, where 1 means I want this the most and 0 means I don't want this at all. If Q isn't specified, it defaults to 1. Hashtag how servers use it. When a server sees multiple options in the accept header, it sorts them first by Q weight, higher first. If there's a tie, it then considers the order they were listed in. The server will then pick the best match among what it can actually produce. For example, if the browser says mesh text HTML Q equals 1.0, application XML Q 0.9.8, then the server knows to send HTML if possible, XML as a decent fallback, and literally anything else only as a last resort. Why this matters. Browsers set these weights to mimic realistic human behavior. Humans expect a web page, HTML, first, but if a feed or API accidentally responds with XML, the browser will still show it. The wildcard with a lower Q is the safety net to avoid total failure if the content type is unexpected. Some servers also use Q factors to decide which format of the same content to send. For example, an image server might look at image AV Q equals 1.0 minus image WebP Q equals 0.9, image JPEG Q equals 0.8, and choose AVF for Chrome because Chrome says it's the top preference. Do you want me to drill even deeper into this, like showing real-world server examples of how queue negotiation changes responses? Or shall we go up and continue with the next property?
I think we're going to go out of this rabbit hole and go up one level. So basically, we're explaining this piece I was saying. That was user agent. No, accept. We were. So this browser accepts these types of things. And now the next property, accept language. I don't actually remember seeing it saying, I don't remember seeing it explaining accept language and no cache. Is it the same? Oh, there's a comma. Okay, it's just my editor. Accept. Oh, you see, this thing doesn't have quotes around it. This one does. Why is that? Could ask it. Okay, now we're going to do accept language. It's probably pretty obvious. Let's read it out loud anyway. So we can say it's accepting New Zealand English. But there's also quality. So we learned about that already. There's quality.
Climbing up from the queue branch, we return to the top-level header list. We've now fully covered the accept property and all of its quirks. Next property is number 3, property name, accept language. You can see the code in our conversation history. This header tells the server the user's language preferences and their relative priority. It uses the same queue waiting system we just explored. Do you want me to start breaking this one down rabbit hole style? First, the NNZ part, then the ENQ of 0.9 part.
Now let's just go to the next one. So when I say next, it's going to go to cache control, which is the next property on the list. Oh, not seeing it. Cache control. Cache control, no cache. I'm going to finally work out how to say that word. What does that even mean? So we're telling the server, but the caching is up to the client, not the server. Where are we doing this caching? Okay. I'm not totally getting it. First of all, I've got to decide where is this cache control happening? On the server? We're telling the server not to cache. Because the other properties are like, we're telling the server that it's English. We're telling the server to return blah, blah, blah. We're telling the server cache control, no cache. We're telling it that we don't want it caching, which means we don't want it saving any data. No, not saving the data, but if there is a page, a static, like an image or something, that the browser, that your client, that you're on a browser, you go there, you see an image of whatever, then you go back there again a second time, seeing the same content, and it's a static content, so it's not dynamically generated. And if you say no cache, the server's going to return it again. But it didn't have to. It didn't have to return it. That's what I think no cache means. What do you guys think that means? So let's go back to the code and have a look how it's right. Think hard. This is war.
All right, let's go straight into the next property after accept language. Number 4, property name cache control. You can see the code in our conversation history. This header is a directive to caches, like CDNs, proxies, or even the browser itself. Despite how it sounds, doesn't mean don't cache at all. Instead, it means you can store the response in cache, but you must revalidate it with the origin server before serving it again. That's different from no store, which forbids writing the response into cache entirely. So with no cache, every time the browser or a proxy wants to reuse the cached response, it has to check back with the server to confirm it's still fresh. Want me to branch deeper into the differences between no cache, no store, and max AG 0? Or should we go up and continue with the next property, pragma?
What the hell? Okay, we wanted to explain this more. I was totally wrong. No cache doesn't, you're not telling the server not to cache. Let's read this again. This header is a directive to caches like CDNs, proxies, or even the browser itself. It is a directive as it's telling the client. It's by how it sounds. No cache doesn't mean don't cache. It means, well, why the hell did they invent it this way? It means you can store the response in a cache, but you must revalidate it with the origin server before serving again. It's a directive to proxies, which means there's another server before the other server, just two computers. First, when you make the request, it goes to a proxy. Let me try and explain it to it and ask it if I'm right. Yo, Tippy, let me try and explain this to you. Make sure I think I'm understanding it. So when we say cache control, we're talking about cache control. Okay, yeah, cache on the server. This is happening on the server. So when we say no cache, we are basically telling the server if that resource, for example, an image, if it can be just returned, if it hasn't changed, if the image hasn't changed, then it doesn't need to send it again. But if it did change, then it will send it back. So a fresh one, only if it's been modified. If it hasn't been modified, the data, it doesn't need to send it again because in the browser it's already got it, so it doesn't need to give it again. Is that correct? Am I explaining this cache control, no cache value correctly? Let's have a look if I'm actually right here. It's definitely going down a rabbit hole. Okay. Didn't write any code yet. Okay, there's my explanation to explaining what it just explained to double check to make sure I've got it. So I may not have it, but it's okay. I may not be explaining it correctly or I don't get it. It says I'm on the right track. Okay. What does that mean? Does that mean I don't get it fully?
Yeah, you're on the right track, but let me tighten it up so it's crystal clear. When the browser or a proxy in between sees cache control no cache, it's not forbidding caching. It's saying you may keep a copy of this resource in cache, but before you serve it from cache, you must check with the origin server to make sure it hasn't changed.
Wait a second. When the browser or a proxy, let's get it to draw a diagram of this. Tippy, draw us an ASCII diagram of this, maybe like a flow chart would do. Okay, we want to get it to draw a diagram Because as soon as they start talking about proxies, it confuses me. Okay, I'm asking it if a flowchart is appropriate. If it's not, then I'm telling it to go think of something else. Oh, cool. It's doing it. Is that? Oh, okay. Okay, let's get it to read it out loud. Follow this flowchart.
Got it. Let's make a clean ASCII-style flowchart to show how cache control no cache behaves. You can see the code in our conversation history. Here's what it shows. If the browser has a cached copy, it doesn't just use it directly. It must ask the server first. That check goes as a conditional request, if none match or if modified since. If the server replies 3.
Wait a second. Let's make it use. We need it to use yes or no flows. So Tippy, update this flowchart and use true and false paths. When true, use a Y. If false, use an N. Put each item in a. Oh, actually, you got a yes. You don't have a negative path. Update the diagram to have a negative path as well. Put each step inside a box and draw it again. If there are any other steps, show them all. I don't think it's actually showing all the steps. I guess this is simple to understand. Maybe the word proxy always confused me. What the hell call it proxy for? Oh, that's nicer, isn't it? Look at that. So we're trying to understand this property. No cache. I thought it's telling the server we don't want a cache, but that's not true. I'm pretty sure maybe what I did just say before is actually correct. So don't let the AI take you on a rabbit hole. Just read it out loud.
All right, let's redraw this properly as an ASCII flowchart. We'll use boxes for each step, diamonds for decisions, and mark the branches with Y, yes, true, and N, no, false. Here's the updated diagram for cache control, no cache. You can see the code in our conversation history. This flow now has both yes and no paths at every decision. If there's no cached copy, it skips straight to fetching fresh data. If there is a cached copy, it asks the server. Then, if the server says not modified, it reuses what it has. If the server says modified, it replaces it with the new copy. Do you want me to now draw a second flowchart for no store alongside this one so you can compare how much stricter it is?
I think that's just what I said. So the browser have cache copy. Does the browser have a cache copy? This is when the cache control is set to no cache in the header. And if the browser, does the browser have a copy of the resource? Okay. Does it have a copy? It doesn't have a copy? Fetch the full resource from the server. And the server is going to return 200, okay. Store the new cache copy. Store the new cache copy. So it's going to store the cache. Okay, and if it's, does browser have a cache? Does the browser have a cache copy of the rest of the resource? It does. It already has a cache copy. How does it know it has a cache copy? So somehow the server knows if it has a cached copy. I guess it tells it. It tells it's got a copy of it when it makes the request. It must do. Send conditional request to server. If no match. If modified since. If it does have a cache copy, it sends a conditional request to the server because it does have a cached copy of the resource, and it sends the date it was modified. Modified since. If none, match. And then, if it's been modified since this date, so it sends the date. It was just last modified. If it has been, I don't know, I'm not too sure about this date thing. It doesn't say anything about date. Basically, if there's a newer resource, then it has been modified. Server says not if it's not modified, then I also did it in a positive way. If it's not modified, if it is modified, if the resource is not modified, it's saying it around the other way. Send the server a fresh copy. That means it was modified. That means we send the server a fresh copy if it was not modified. If it was not modified. If it was not modified, yes. Yes, it was not modified. You see? Wait a second. Your tippy, explain this diagram using positive paths. For example, don't test by false conditions. Don't say server not modified. Say modified. And then swap the Y and the N condition. So it's easier to understand this diagram. Yes. Explain paths with a positive, not a negative, and redraw this diagram. This will make it easy to understand. I guess it's simple, but it's okay. What's this doing down here? I think I broke this diagram. I think we need to move on. Okay, I did do what I said. Server says modified. If it is modified, see, this pointing to the wrong place. It should be this box. Yes. If it was modified, server sends a fresh copy. Modified? No. Then it reuses the copy. It sends a 303. 4. Right? And it only does this. That's if the client, does the client have a copy of this resource? That's what I said before. You can get it to read out loud.
Got it? You want the flow described in positive terms instead of negatives. So instead of asking server not modified, YN, we flip it to server modified, YN. Same logic, but phrased in a way that the yes path is the active positive outcome. Here's the updated ASCII flowchart. You can see the code in our conversation history. Hash, how this reads.
I think maybe we need to get out of this. Okay, we're done with this no cache thing. I got it. We got it. Let's go back up a level. This is actually the key piece anyway to making this crawler work. The rest of the code, you can see, it's just a fetch. We just send the header, basically. And there's a function here to crawl the website for seed URLs. So these are defined URLs. Result put. I can actually map that out. Let's do something different. I think I'm done with that header. Probably no catch. Where are we? Oh, that's this piece. Let's just quickly go through these things. But then we won't fully understand it. I think this one's easy to understand anyway. Let's just read it.
All right, climbing up one level from the deep dive into cache control. That means we've wrapped up property 4. Next top level property is to number 5, property name Pragma. You can see the code in our conversation history. This one is basically a historical twin of cache control. No cache, but for HTTP 1.0 compatibility. Old proxies and caches from the early web days didn't understand cache control, so browsers sent Pragma no cache to cover both bases. Modern servers mostly ignore it, but browsers still include it alongside cache control to look authentic. Do you want me to drill further in?
Hmm. It was so no cache. Pragma is the same as cache control.
All right, moving on to the next top level property after Pragma. Number 6, property name, upgrade-insecure requests. You can see the code in our conversation history. This header is a signal from the browser to the server saying, if this page has insecure HTTP resources, please upgrade them to HTTPS if possible. The value 1 just means true/enabled. There are no other values defined. It's either present with 1 or not sent at all. Servers or CDNs that support this will automatically rewrite links, images, or sub-resources from https// to https/. Combined with security policies like Content Security Policy, CSP, it helps prevent mixed content warnings in modern browsers. Do you want me to drill deeper into how servers act on this header, like CDNs forcing HTTPS and how browsers handle mixed content, or move up to the next property?
Explain this in a different way. More information.
All right, let's go deeper and paint the whole picture of upgrade insecure requests. 1. What it is. This header is the browser politely telling the server, I prefer secure connections. If you're about to give me a page that includes insecure stuff, please rewrite it to HTTPS instead of HTTP. It's not a hard block, it's a hint, but one that most modern servers and CDNs respect. Why it exists. The web went through a long transition from HTTP, unencrypted, to HTTPS, encrypted. A big problem during that shift was mixed content. A secure page, HTTPS, loading insecure subresources, HTTP images, scripts, iframes. Browsers throw warnings or even block those resources because they could be tampered with. By sending this header, the browser is saying upfront, don't bother giving me insecure URLs. If you can, automatically upgrade them to HTTPS. How it works in practice. Imagine you visit an HTTPS page that has imgexample.com//foo. 1. Without this header, the server delivers the HTML as is. Browser requests the image over HTTP. Browser may show a mixed content warning or block it. 2. With this header, server CDN sees the browser supports upgrades. It rewrites that URL to /example.com/foo.png before sending the HTML back. Browser never even tries the insecure version. It's auto-secured. Where it's most useful, CDNs like Cloudflare or Akamai, they can auto-upgrade insecure requests to HTTPS when they see this header. Content security policy. There's a directive upgrade insecure request that does the same thing on the client side. The header here is like the browser saying, yes, I support that behavior. Legacy sites. If a site still has some HTTP links hard-coded, this helps smooth the user experience while they migrate to HTTPS. So heck it, why the value is 1. It's just a Boolean switch in string form. 1 equals enabled, upgrade requests. If the header is absent, upgrades aren't requested. There's no 0, true, or false option. So in plain terms, it's the browser's way of saying, I want you to give me HTTPS for everything, even if you originally wrote it as HTTP. Please rewrite it for me so I don't have to see scary warnings. Do you want me to show an example of a real server response?
Interesting. Next.
All right, moving up from upgrade insecure requests, the next top level property is number 7, property name secfetchSite. You can see the code in our conversation history. This is one of the fetch metadata request headers that browsers add automatically. It tells the server what the relationship is between the page making the request and the resource being requested. The value none means the request wasn't triggered by another site at all. It looks like a direct navigation typed in the address bar, clicked from a bookmark, or opened a new tab. Other possible values are same origin, same exact origin, same site but different subdomain, or cross-site, completely different site. Servers and CDNs use this header for security checks. For example, they can reject suspicious cross-site requests to protect against CSRF, cross-site request forgery, or they can allow only same origin navigations for sensitive resources. Do you want me to drill deeper into all the possible values of secfetchSite with examples, or move up to the next property, secfetch mode?
What the relationship is between a page page making request and the resource being requested. The unknown means the request wasn't triggered by another site. It looks like a direct navigation typed in the address bar. Click the book bar or open new tab. So it's the same sick fish. Okay, why do I call it? Why the fuck it's called sick? Let's explain all these sick ones. Explain its sick properties. As you can see, there's a bunch of sick properties here. No, actually understand this before moving on. This is the hardest piece to understand in the code.
Ah, got it. You mean explain exactly the 4 secfetch properties you've got in your code, not the whole family. Let's break each one down clearly. Secfetch site none. This means the request wasn't triggered by another site. In practice, it looks like a direct navigation. The user typed the URL in the address bar, opened it from a bookmark, or launched a new tab. If it came from the same site or a different site, you'd see same origin, same site, or cross site instead. # sec fetch mode navigate. This tells the server the mode of the request. Navigate means this is a top-level page navigation. The browser is loading a whole page, an HTML document. Other modes like cores or no cores would apply to subresource fetches, but here it's clearly a page load. Secfetch user, tot1. This indicates whether the request was triggered by an explicit user action. The value 1 is basically a Boolean yes. It shows that the user clicked a link, hit enter, or otherwise caused this navigation. If it's missing, it usually means the navigation was automatic, like a redirect or a script-initiated fetch. SecFetchDest document. This describes the destination type, what the resource is meant to be used as. Here it's document, which matches the navigate mode. It tells the server that the browser expects a full HTML page. If this were an image, script, or style, you'd see image, script, or style instead. Put together, these four say, open quote, this is a user-triggered direct navigation to fetch a document, a full HTML.
Add some full comments to this code. Each property and value. The value is another property. Expanding values to this code. Next code copy box. No. Hmm. Lucky. Uh-huh. The fuck with a fucking going. Okay, Tiffy, let's change topics. Let's write some call code for pack and save. Let's do pack and save now. We'll connect it to the database later.
Nice, spinning up packing safe now. DB can come later. I dropped in a clean, fully typed crawler lib plus a Next.js app router endpoint that returns JSON, no persistence yet. It politely fetches category detail pages, prefers JSON LD, schema.org product, and has a small HTML fallback. Inputs are validated with Zod, no any's. I've put the complete files on the canvas. Lib crawl packingsafe.ts, the crawler library, polite delays, JSON LD extraction, strong DTO. API slash packingsafe slash route.ts. Post endpoint, auth key seed URLs, max pages, min delay, emis, max delay emis, returns products meta. Want me to wire quick curl smoke tests next, or you want to try it against a couple pack and save category URLs first? Got it. Your endpoint works fine, but Pack and Save servers are returning 403 forbidden when our crawler tries to fetch the page. That means their bot wall doesn't like the headers we're sending. Right now, we send only the basics, user agent, accept language, etc. Woolworths let that through. When we hit a category page like tested in, you can see the code in our conversation history dot. The server should return a normal HTML document with lots of script type application/LD JSON blocks. Inside those JSON LD blocks are at type product entries. That's how we know we're dealing with real products with name, price, brand, image, etc. Ah, that explains it. The 403 wasn't really about headers. The URL itself is wrong. In your browser screenshot, you can see the code in our conversation history that returns a 404 not found. So the crawler is faithfully reporting what the site gave back. Pack and Save's category structure is different from Woolworth's. They don't have rice, pasta, noodles/rice. To fetch real products, we need to start from a valid category or product URL that actually. Great, that gives us what we need. Here's the game plan. We'll crawl real product listings and be confident the crawler works correctly. 1. Valid seed URLs to use. Based on browsing the site, these category pages are actively serving product data. Dried pasta and rice section. /www.packandsave.co.ns shop//category/pantry/rice-noodles rice pack and save. Great, that gives us what we need. Here's the game plan. We'll crawl real product listings and be confident the crawler works correctly. 1. Valid seed URLs to use. Based on browsing the site, these category pages are actively serving product data. Dried pasta and rice section. /www.packandsave.co.ns shop//category/pantry/rice-noodles rice pack and save. Instant rice /pat.co.ns/shop category//pashed rice noodles /instant rice PG = 1. Pack and save creamed rice desserts category /shops category pantry desserts creamed rice Pack and save these return real listed products with full HTML and JSON LD. Perfect targets for crawling. Part 2. How we'll crawl it. 1. Fetch a seed URL with strong browser-like headers, including sexy US, cfetch shot, etc. 2. Extract all script application SOM blocks from the response. 3. Parse each JSON LD block to find objects where @type or type includes product. 4. Validate each object using the ZOD schema, ensuring clean title, price, image, etc. 5. Return a list of product DTOs and crawl metadata. Next steps. Update the crawler file to include realistic Chrome headers so Pack and Save serves HTML correctly. Test it via curl against one of the valid seed URLs above, e.g., you can see the code in our conversation history. If everything works, the API will respond with structured product data instead 403s are coming from Pack and Save's edge, not our code shape. Let's ship a pragmatic fix. Try a few realistic header profiles with refer, origin, and UA hints, and fall back between them on 403. Drop this into your libcrawl packandsave.ts. It replaces browser headers and fetch page.